welcome in nuclear fission, kind of the introduction to it, and the concept of mass energy equivalence. So I want to talk about in this video kind of two key concepts before you start jumping into nuclear fission. Those two key concepts are related to mass defect and binding energy, and how do those relate back to the mass energy equivalence. So those are the two items that we want to be able to discuss. I will try to also highlight them through an example in terms of a calculation. So first off, as you can see there on the screen, I bring back the law of conservation. And when you do talk about the law of conservation, when you're going way back into mechanical energy, then you typically just talk about energy, period. Well, there's this amazing equivalence between mass and energy. So if you go really deep down and you start studying kind of nuclear reactions, nuclear fission, and you take the nucleus apart, you notice that the masses and energies relate back to each other in some particular way. So you'll see that in this video. So when we talk about the law of conservation of mass energy, this is what we are referring to. So what we're saying is nothing different than before. We do have an isolated system, which means we're not going to be adding any more mass to it. We're not going to be removing any mass from it. We're not going to be adding any energy into it, and we're not going to be removing any energy out of it. It just means it's self-contained. So we have an isolated system on its own. And if you have that, then it turns out that the mass and the energy can transfer into one another to go back and forth between mass and energy. And the total mass energy that remains is constant. Now, this isn't really anything new, because if you think back of energy, period, so forget the mass concept, you knew that energy can't be really created, it can't be destroyed, it can only be transferred. Yet now we're bringing in and we're saying that this whole concept between mass and energy is tied in together. So if there is some mass missing, it must be in terms of energy. If there's some energy missing, that means that it's actually transferred into mass. So it goes back and forth between each other, and it remains constant in an isolated system. So that's what this law of conservation is. So it's a carry forward from all the things all the way back to mechanical energy, which you have been seeing over and over again. So that's the first concept. Now, let's dive into this binding energy. So what about this binding energy, and what exactly is this binding energy that we will have? Well, binding energy on its own, so if you're thinking about this, this is simply the amount of energy that you would need in order to break apart the nucleus of an atom. And as you know, the nucleus itself is made up of protons and neutrons, or nucleons, okay, if you just use the general term. So protons and neutrons are bounded in, and they're held together by certain nuclear forces that you have. And those particular nuclear forces that you were having, so this kind of goes back to these nuclear reactions that you've also studied. I can put up a link up above there if you've forgotten that. So those particular forces are held in together, and in those bonds between those nuclear forces, there's energy there. So the binding energy on its own is the energy that is needed in order to break apart these protons and neutrons from being clustered together in the nucleus. Or it is the energy which is released. So it is the amount of energy that would be released when you do take the nucleus and you create, so meaning protons and neutrons, and they start to come together. So it is actually either the breaking apart, okay, which is typically kind of the fission concept. Coming in together is kind of the fusion concept as well. So that's what you have within there. So it is either to break those bonds up, okay, or to create, okay, those bonds up, and then it's the energy which is released. It is a good measure, okay, of strength, of the stability of a nucleus in particular. That binding energy is interesting because that energy that you can find is going to be kind of the missing link between the mass of the actual entire nucleus. So you can capture the entire nucleus based on the energy and the mass, and hence the equivalence between the two. So let's dive a little bit deeper. So we know that this is the energy which is holding these things together, okay, or is needed in order to break them apart. So if you carry forward, now I want to dive into this whole concept of mass defect and then tie it into energy. So what is this mass defect in these mass energy equivalences? Well, the mass defect is nothing else but the difference between the mass of the atomic nucleus of its own. So if you take each individual components, okay, and the actual sum, okay, so that you would have of those components in comparison to the atomic nucleus mass itself. So if you take each atom, so whatever atom it might be, I'm going to do an example, for instance, with copper. So if you take that copper, it's going to have a certain atomic mass. So that atomic nucleus is going to contain a certain amount of mass. And then you can also take individually all of the protons and the nucleons and the neutrons, okay? So as you add them up together, so all of those individual items, so all the nucleons all together, then you can see what is the difference between the actual mass of the atomic nucleus, and then what is it that when I sum them up all together, what does that come up to? And what you will find is that the two are not equivalent. So they're not the same. So there's a difference between adding them up individually, protons and neutrons, getting a mass, and then taking a look at the nucleus itself and saying, what's the atomic mass? That difference between the two is called the mass defect. So it's like a difference in between. It's not something that we would expect. So the question is, where is this difference? That difference that we have is actually the binding energy. So that binding energy is that difference between the two. And it's that energy that creates this equivalence between masses and energies that we have. Now, be careful, because depending on which textbooks you read or where you look this up, normally when we're adding up individual components of the nucleus, we are just talking about the nucleus, so meaning the protons and the neutrons, so nucleons in general. However, sometimes some textbooks, okay, and in particular on the high school side, you might see that they might also add the electrons, which are circling around. Now, technically, the electrons are extremely tiny in comparison to protons and neutrons. So even if you would add them and you start talking about a certain amount of significant figures, they won't really make that big of a difference. However, we don't normally add this. So if you carry on into post-secondary, you'll notice that we don't talk about the electrons in mass defects. It's just the nucleons that we have. So I am not going to be adding these in the calculations. All right, so you won't have this because I'm just talking about the nucleus itself. Now, if you carry forward this, so this particular difference, so what it is, notice I have defined it over here. I said that it is the mass of the nucleus, okay, is less than the sum of the individual nucleons. Okay, so this difference is the mass defect. All right, so let's highlight this out. The mass of the nucleus, so that's like your atomic mass in general. Again, the electrons are negligible. So if you just take that atomic mass, so that mass of that entire nucleus is going to be, interestingly, less. So it is less than the actual components that we have. So if you take the sum of the individual components of the nucleons and the electrons, if you just had them individually, and I'm going to remove the electrons in here, as I said. So I'm going to kind of remove this, but do be careful because sometimes some textbooks will add it. So if you do that, then that mass of the nucleus is less. So why would that be? Well, the reason is because if you bring these things into a nucleus together, it is actually the difference in between these individual components if they were separated all apart. So if they were separated all apart, they have a certain amount of mass. But if you bring them together, you've now created the nuclear bonds that are there. So the nuclear forces are start to creating in it. And what happens is that is the mass defect, the difference between being individually apart and being bound in together as a nucleus on its own. And that difference we can find out and calculate. And that defect itself, so what happened, it's not like the mass has disappeared. No, the mass did not disappear. But what has happened is the mass has been captured in the binding energy within to hold this thing together. That's what has happened. So that is the mass defect and the equivalence between your actual mass and the energy. So in particular, it is the mass defect and the equivalence to binding energy of these things coming together. And it is released, okay, or captured in these nuclear fissions, okay, or fusions, okay, although here we're talking about fission, which is breaking these things apart, in this famous Einstein's equation, which basically captures and does an equivalence between energy and mass. And it is that energy is equivalent to mass multiplied by c, which is the speed of light in a vacuum squared. And that is captured within, and we can see that through experimentation, where these two things are now bound together. That is now the equivalence between your mass and your energy. And it is between the mass defect, okay, and the binding energy. So this is where it goes back and forth in between each other. All right, so that's what we have. Let's take a look here, and I want to just give you a little table first, okay, that I've created, and a couple of comments in here. So here's a summary. So if we're going to be jumping in and we're going to do these calculations, and I will do one of them just so that you can understand that this mass defect is nothing major. It's not very difficult to find, especially nowadays because we have pretty good approximations of all of these different particles. So here is a table where I'm presenting all the particles. So here's an electron. This is just for kind of completion's sake. This is a neutron and then a proton. And here in the middle, I am describing masses, right? So these masses in metric standard SI units, they are in kilograms. Now, an electron, neutrons, and protons, they're tiny, right? But here they are. These are all captured. So these particular ones are captured. And I actually looked them up. I put them in kind of OpenAI's ChatGPT, although you can look them up pretty much anywhere, all right? So that's what they are. You can keep as many significant figures as you have. They might change ever so slightly, okay, as time goes on and we have a better, okay, and better tools to try to approximate these, okay, and measure them. But they are very, very tiny, as you can see here, okay? So within, so if you look here, this is 10 to the negative 31, 10 to the negative 27, and so on. And the first thing that I'll mention to you is notice how much smaller an electron is, right? Minus the exponent minus 27 and minus 31. That's 4 orders of magnitudes. That's massive. Okay, so even if we would start to include electrons, okay, anywhere, its mass is puny, okay, and very negligible. Now, the highlight in here is that this table captures actually mass between kilograms and atomic mass units. Now, atomic mass unit has been defined, okay, and it is equal to within the carbon 12 atom. And one atomic mass unit has been defined as 1/12 of this. So 1 out of the 12, so that is for the carbon 12 atom. And it is equivalent to approximately, as you can see there, 1.66, etc., times 10 to the negative 27 kilograms. Now, if you've studied chemistry, you've seen atomic mass units. but they are coming from the actual masses. And they're much more convenient to utilize when we're at such a small scale. When we're just talking about atoms, we don't want to be talking about kilograms, because kilograms are monstrous, right? And they're made up of many different particles, okay? Gazillions of them. So we want a more convenient unit when we talk about mass on such a tiny, tiny scale. Sure, we can use scientific notations, but even that, it's not very convenient for us to use. So we prefer to actually use the atomic mass unit. And in here, so notice the comparison between an electron, a neutron, and a proton. So a neutron is a little bit bigger than a proton, not very much. But you can see that a neutron and proton are much, much bigger than an electron. So that is where the atomic mass unit is coming from, if you ever wondered. It is related back to the carbon-12 atom, and it is just 1/12 of it. And then we compare it to all of the other atoms or elements, okay, that can be created depending on how many protons they carry. All right, so that's the first note. Now I wanted to present this to you because if we're going to be talking about mass defect, so the difference, we're going to be talking about, okay, what is the difference of masses between the isolated individual items if you sum them up and when they're all bound together, okay, within their nucleus. And that the difference we want to calculate. And we can do it both in kilograms and in atomic mass unit, which is a little bit more convenient for us. But we need the relationship between the two, because if you do start utilizing this equation, this does assume that you are going to be using in here metric standard SI units. So we need kilograms within here, okay, in order to do that. So we need that difference, okay, within. So we need the actual unit conversions right there. Here's a little second note. So at times, as you're going through and as you studied energy, you will recall that the SI unit for energy is the joule. But again, now, joule in general is not a very big unit. But if you're going to be talking about kind of these very tiny scales where you're talking about atoms, and then the energy that's within just one single one or a few of them, then it's not going to be very much. Of course, if you have 1 gram, well, now you're going to be talking quite a lot of energy within there. But what we have done is, again, this is just for convenience, when you are talking about a very small nuclear interaction scale, joule is not very convenient. So we use electron-volt as one of our units. The unfortunate part is that you may run into this before actually studying electricity in general. So you may not know what a volt is. That's okay. You're very familiar with units, so you understand that there might be different units on different scales that we use just for convenience. So it turns out that with respect to kind of these electrons, let's think about electrons. So the amount of energy that they might carry, so 1 electric volt, is equal to this tiny amount in terms of joules. But of course, on a very tiny scale, well, you're not going to expect huge amounts of energy. Now, another convenient way, so in terms of electron volts, we do mega. Now, mega is a prefix. So that's 10 to the 6. Right? So it's 1,000,000 of these electron volts. So as you can see there, the actual combination between the two, so if you go from here to here, notice this is negative 19 plus 6 on the exponent side is going to give us negative 13, and that's going to be just a mega. Okay? So you've seen, hopefully, prefixes. Okay? If you want a refresher, I'll put up a link up above there on prefixes for you, so that you're back in kind of understanding, okay, with regards to those. So that's another note. So we have masses, we now have kind of energy components, and now here's the final component, which is related towards this energy and mass. So back to this kind of Einstein equation of energy is equal to mass times c squared. So this mass-energy relationship or equivalence in between is indeed captured in this way. Now, the one thing that I wanted to point out, again, now this is pretty much, okay, a constant of nature, which is the speed of light, so c, which is the speed of light, In a vacuum, we have found what it is, and it is about 299, so 299 million, okay, 792,458 meters per second. That's how fast, okay, light is actually traveling. And often, this is not very convenient to remember, so we use an approximation, which is 3 times 10 to the 8 meters per second, which is much easier to remember. Of course, that is rounded, right? So this is just the 3 significant figures, but here is the exact natural value of the speed of light. Okay, let's try to bring all of this stuff together so that we can see how all of this relates. So here is an example. An example is rather simple. So it says, what is the mass defect and the resulting binding energy equivalence for copper-63? And here, the nucleus, or the atomic mass, is provided to us. So we have that the atomic mass, for this copper-63 is 62.9295, etc. Now, of course, when you look this up, as you can see here, and you take a look at the actual periodic table, you'll often find that the atomic masses, are different than for the individual isotopes. Please remember, again, that copper has, it's not just one isotope. So therefore, when we take this as our atomic mass, this is just the average between the isotopes that are found in nature, at least up to this point, right? This is what we found, as an average between the isotopes. This value is different, than this because it's for a specific isotope that I'm giving you. So this is of the actual nucleus itself, all right? So let's assume that this is the mass of the nucleus when it's bound up together. Now, what we're going to do is, in order to find the mass defect, so if we want to find what the mass defect is, so let me just abbreviate it in here. I'm going to say that this is the change in mass. I'm going to put this in and put a little d for defect. Then what this is going to be is, it's going to be, first, we're going to have to find what is the mass of all the protons in that copper atom that we have, plus what is the mass of all the neutrons. And again, I'm not going to be adding the electrons in here, all right? So be careful, double check, okay? We should not be necessarily adding these in. So that's something which is standard. If you do find that the textbook utilizes it, that's not normally done. So this is what we have. That's the total. This would be if you had them individually. So these are broken down individually. That's what would happen if you broke these up and you would find them on their own. Now the difference is we're going to have to try to take this and subtract it from the actual mass. So this is the mass, so the atomic mass in here of that nucleus that we have. And you'll see that this right here is indeed less, than the actual components individually. Because when you bring them all together and you bound them in, there is binding energy which is going to be causing this mass defect in. So on the individual side, so if I want to take this, we already have this is given to us. So now we have to figure out what this is. Well, so copper, so we have 29 of these protons, right? So we're going to have to multiply it by the mass of each proton. So let's take a look in here. So I'm going to go back, and now you can use as many significant figures as you like. So, if you're looking this up, it might not have as many as here, and it might be slightly different. Of course, depends when you're watching this video. So this might get updated. So I'm going to do this. So this is going to be all my protons. And by the way, so indeed, now for atomic mass units, we can designate it with a U, which is typical. Sometimes you see it as AMU as well. Now, I also need within here all of the neutrons in here. In order to calculate. So this is, well, they tell us it's copper-63. So 63 minus the number of protons in here. So if I take these out, so 63 minus 29, I guess is going to be 34. So So that's going to be the amount of neutrons that I have. So 34 times. And again, I need the individual mass of the neutron. So I'm going to take this, okay, copy it out within there. And I'm going to place it right there. So that's what you have right there, okay, within. And again, so the unit here, so this is just simply atomic mass units. This also is given in atomic mass units. So that's what we have within here. So AMU, or just simply U, okay, in terms of that. All right, so let me do that calculation and add these up together. So I'll do that quickly. You can punch it into your calculator as well. So here we have it, all right? So I put it into the calculator, I've added them up, and this is what I get. And notice that it is indeed bigger on the individual side than it is when it is bound together in the nucleus. So this one was given to us, so that's right there, so this is what we have. And this one we calculated on the individual components. Again, you can round to whatever it is that you like, I just kind of left them. Now, the mass defect, so the actual mass defect that we have, is going to be the difference between the two. So if you take now these two and you subtract them, you're going to get the mass defect. And that mass defect in between has now transferred into the binding energy of that nucleus. So that nucleus is going to be carrying in, and that mass, this is the mass and energy equivalence between the two. So let me just do this subtraction, okay, and let's see what that will be. So there you go, okay, so this is what that is. Now we can take this in and transfer it, because I want to be able to now show you that you can take this and create the binding energy, or sorry, find the binding energy that is captured in this mass defect, and that is nothing else but simply energy is equal to the mass times c squared, where our mass is indeed the mass defect right there. So that is what that energy is captured in, and we can do this utilizing our equation. However, we do need the metric standard unit, so I can't keep this in atomic mass units. I have to change it back. So I will have to go back in here, and I'm going to take this in. Okay, so I have it on the calculator, and I'm going to now substitute. So notice right here, I'm going to do the unit conversion in between the two. So this is what I have. So I will take that answer and multiply it, okay, because I want to be able to get it. So let me just actually put it in brackets, 1.660539040 times, this is going to be 10 to the exponent of negative 27. So it's going to be a very tiny amount, so it seems, but again, this is just for one nucleus. So that's what I have. And I'm going to just leave it on my calculator right there, because I don't want to go back in and change it and kind of write it all out. So that's what we have, and we can, put that right in there in terms of keeping it in kilograms, and that's what we would have. Now I want to take this amount and substitute it. So I have my mass defect, which I've just found, which is the difference. Now I have to multiply it by c squared. So I have to take this multiplied by, now the speed of light, again, if you're going to be using 3 times 10 to the 8, okay, so that's easier. I'm going to just actually input it in because I have it right in front of me. So this is easy for me to put in. And now don't forget, please, okay, we have to square it because otherwise we're going to get the wrong amount. So this is how much binding energy that has been converted from the mass. This is the equivalence that I have. So I'm not going to, this one, I'll just leave maybe, okay, with 3 decimal places right there, times 10 to the negative 11. But this is indeed joules. So if you wanted, because joules, okay, is pretty huge for one little nucleus, okay, that we would take. So that is the reason why we introduce these much smaller units, okay, on these nuclear scale sizes. and you can use electron volts or mega electron volts. I'm going to use mega electron volts to convert this back in. So I'm going to take this and I'm going to convert it back. So I'm going to divide it by, so I'm going to be taking this right here to change it into mega electron volts. So I have that. So 1.602176634, and that's going to be times 10 to the negative 13. All right, so I'll put that in. There you have it. So this is what we would have. So that particular conversion, okay, so as you're going through there, is about 530, let's put 7 mega electron volts. That's what you would have in that one nucleus. So that is a very nice example in order to be able to see how these things get calculated. And then of course you can hopefully be comfortable on the unit conversion side, where you can go back and forth between kilograms, atomic mass units, joules, and electron volts or mega electron volts. All right, so that is it for this particular video. I hope that you found this useful and it gives you some kind of a gauge of understanding mass defect and binding energy and understanding how they are an equivalence between each other. Thanks for watching. We'll see you in a future video. Bye, everybody.